There are several possible reasons why a non-contact voltage detector might indicate the presence of voltage on a wire when the circuit is supposed to be de-energized and fuses are removed. The most common possibilities are induction, capacitive coupling, or a faulty detector. Let's explore each of these in detail. Firstly, induction can occur when the voltage detector picks up electromagnetic fields from nearby energized conductors. Even though the circuit you're testing is de-energized, if it runs parallel to other live circuits, the electromagnetic field from those live wires can induce a small voltage in the de-energized wire. The non-contact voltage detector is sensitive enough to pick up on this induced voltage, giving you a false positive reading. Secondly, capacitive coupling is another phenomenon that can cause a false voltage reading. This happens due to the stray capacitance between energized conductors and the ground wire or other nearby metallic object. Capacitance is the ability of a system to store electrical energy in the form of an electric field. In electrical wiring, the conductors and the surrounding materials act as capacitors. When energized conductors are close to de-energized conductors or grounded objects, a small amount of voltage can be transferred through this capacitance. This small voltage potential on the de-energized wire can be detected by the voltage detector. Thirdly, the voltage detector itself could be faulty. Non-contact voltage detectors are useful tools, but they are not always foolproof. They can be affected by environmental conditions such as humidity and temperature, and they can also degrade over time. A faulty detector may give false readings, indicating the presence of voltage when none is actually there. To accurately troubleshoot the issue, here are several steps to follow. 1. Ensure complete power removal. Double-check that both fuses are indeed removed from the circuit you are testing. Additionally, confirm that the corresponding circuit breaker is also turned off. This ensures that there is no intended source of power to the circuit. 2. Use a different voltage detector. Try using a different non-contact voltage detector to verify the reading. If the second detector also indicates the presence of voltage, it is less likely that the first detector is faulty. This step helps you confirm whether the issue is with the detector or the wiring system. 3. Check for loose connections. Inspect all the connections in the circuit, including those at the pole base, the ballast, and the lamp holder. Loose connections can create high resistance points, which can lead to stray voltage readings. Make sure all connections are tight and secure. 4. Examine the wiring for damage. Carefully inspect the wiring for any signs of damage, such as cuts, abrasions, or insulation breaks. Damaged wiring can allow current to leak, creating voltage readings where they shouldn't be. Pay close attention to any areas where the wiring may have been exposed to physical stress or environmental factors. 5. Verify the grounding system. Ensure that the ground wire is properly connected and has a good path to ground. A poor grounding system can allow stray voltage to accumulate. Use a multimeter to test the continuity between the ground wire and a known good ground point. 6. Use a multimeter for voltage measurement. Use a multimeter to measure the voltage between the suspected hot wire and ground. A non-contact voltage detector can sometimes give false positives, while a multimeter provides a more accurate measurement of the voltage level. If the multimeter reads 0 volts, it is likely that the non-contact voltage detector is giving a false reading. 7. Check for nearby electromagnetic interference. Be aware of any nearby sources of electromagnetic interference, such as transformers, motors, or radio transmitters. These devices can generate electromagnetic fields that can affect the readings of non-contact voltage detectors. Move the detector away from these sources to see if the readings change. 8. Consider environmental factors. Environmental factors such as humidity and temperature can also affect the readings of non-contact voltage detectors. High humidity can increase the conductivity of the air, which can lead to false positives. If the environment is particularly humid or damp, try drying the area before testing. 9. Test with a known voltage source. To ensure that the voltage detector is working correctly, test it on a known voltage source, such as a properly functioning outlet. If the detector does not respond to the known voltage source, it may be faulty and needs to be replaced. 10. Consult with a qualified electrician. If you have tried all of the above steps and are still unable to resolve the issue, it is best to consult with a qualified electrician. A qualified electrician has the knowledge, skills, and equipment to properly diagnose and repair electrical systems. They can identify any underlying issues that may be causing the false voltage readings and ensure that the electrical system is safe and functioning correctly. Understanding induction involves recognizing that it's a phenomenon where a changing magnetic field induces a voltage in a nearby conductor. This is the principle behind transformers and generators. In the context of electrical wiring, if a de-energized wire runs parallel to an energized wire, the alternating current in the energized wire creates a changing magnetic field around it. This changing magnetic field can then induce a voltage in the de-energized wire, even though there is no direct electrical connection between the two wires. The magnitude of the induced voltage depends on several factors, including the distance between the wires, the length of the parallel run, and the amount of current flowing in the energized wire. Non-contact voltage detectors are designed to be sensitive to these induced voltages, which can sometimes lead to false positive readings. Capacitive coupling, on the other hand, is a different phenomenon that involves the storage of electrical energy in the form of an electric field. In electrical wiring, the conductors and the surrounding materials act as capacitors. When two conductors are close to each other, they form a capacitor. The capacitance between the conductors depends on several factors, including the distance between the conductors, the area of the conductors, and the dielectric constant of the material between the conductors. When an alternating voltage is applied to one of the conductors, a small amount of charge is transferred to the other conductor through the capacitance. This creates a small voltage potential on the second conductor, even though there is no direct electrical connection between the two conductors. Non-contact voltage detectors are also sensitive to these capacitively coupled voltages, which can also lead to false positive readings. To further elaborate on grounding systems, it is critical to ensure that the electrical system has a properly functioning grounding system to prevent the accumulation of stray voltage. The ground wire provides a low impedance path for fault current to flow back to the source, which helps to trip the circuit breaker or fuse and to energize the circuit in the event of a fault. A poor grounding system can allow stray voltage to accumulate, which can lead to false voltage readings and potentially dangerous conditions. To verify the grounding system, use a multimeter to test the continuity between the ground wire and a known good ground point, such as a metal water pipe or a grounding electrode. The resistance should be very low, ideally less than 1 ohm. If the resistance is high, there may be a problem with the grounding system that needs to be addressed. The NEC, or National Electrical Code, provides detailed requirements for grounding electrical systems to ensure safety and proper functioning. Section 250 of the NEC covers grounding and bonding requirements. In particular, NEC Section 250.4 provides general requirements for grounding electrical systems, including the requirement that the grounding system be designed to limit the voltage to ground and to facilitate the operation of overcurrent protection devices. Section 250.24 covers grounding requirements for separately derived systems such as generators and transformers. It specifies that the grounding electrode conductor must be sized in accordance with NEC Table 250.66, and that the grounding electrode must be connected to the system neutral at the source. In the 2008 edition of the NEC, which may be applicable to the installation, specific tables and sections would provide guidance on conductor sizing and grounding electrode requirements based on the system voltage and fault current levels. Ensuring compliance with these NEC requirements is essential for maintaining a safe and reliable electrical system. Additionally, voltage detectors have limitations that need to be understood. Non-contact voltage detectors are designed to detect the presence of alternating current voltage without making direct contact with the conductor. They work by sensing the electric field that surrounds energized conductors. However, these detectors are not always accurate and can be affected by various factors such as the distance from the conductor, the presence of other nearby conductors, and the type of insulation on the conductor. Non-contact voltage detectors are also not able to detect direct current voltage. When using a non-contact voltage detector, it is important to follow the manufacturer's instructions and to use it in a safe and responsible manner. Always verify the readings with a multimeter before working on any electrical circuit. Additionally, understanding the voltage range of the non-contact voltage detector is crucial. The Greenlee GT-11 voltage detector, with a CAT4 rating of 50 volts to 1000 volts, is designed for testing higher voltage circuits. The CAT4 rating indicates that it is suitable for use in environments with high transient overvoltages, such as at the service entrance or on outdoor conductors. It is important to use a voltage detector that is rated for the voltage level of the circuit you are testing. Using a detector with an insufficient voltage rating can be dangerous and can lead to inaccurate readings. Therefore, for a 240-volt single-phase street fixture, a detector with a CAT4 rating and a voltage range that includes 240 volts is appropriate. However, it is still important to verify the readings with a multimeter to ensure accuracy. In summary, when troubleshooting a situation where a voltage detector indicates the presence of voltage when none is expected, consider the factors of induction, capacitive coupling, and potential faults in the detector itself. Follow a systematic approach, ensuring complete power removal, verifying with multiple detectors and measurement tools, and checking for common issues like loose connections or damaged wiring. Always prioritize safety and consult a qualified electrician if the problem persists or if you are unsure about any aspect of the electrical system.